So, welcome to module 25. In this module, we will introduce the concept of conditional expectations. We have already introduced the concept of conditional PDFs, conditional probability mass functions or conditional distributions. Using the notion of conditional PDF or PMF, we will introduce the concept of conditional expectation. So, suppose you have a random vector x, which itself comprises of two random vectors y and z, where y is a p1 dimensional, z is p2 dimensional. So, your x is a p dimensional random vector, where p is same as p1 plus p2. Now, this could be the discrete or absolutely continuous. So, that is why we are saying that y is a p1 dimensional vector with PMF or PDF Fy, z is a p2 dimensional random vector with PMF or PDF Fzz. So, x is either absolutely continuous, in that case it has a PDF, or it is discrete, in which case it has probability mass function. So, we have seen that if, let us say, for given z belonging to Sz such that Fzz is positive, the conditional PMF or PDF of y given z is equal to z. So, I am talking about the conditional probability mass function or conditional probability density function of y when z has been fixed at a point small z. So, this is same as a joint PDF of y and z divided by the marginal of condition 1, and marginal of condition 1 is Fzz. Note that in this expression my small z is fixed. So, it is a probability mass function at the point y. So, it is a function of y. So, for me that means this is a constant, this is a fixed quantity. So, this is same as kz times fyz fy for y belonging to Rp as a function of Rp, because z is fixed, and this kz is nothing but Fzz inverse, and this is a normalizing constant. It has to be normalized in such a way such that for a fixed z, when you sum or integrate this quantity, the sum or integral turns out to be 1. So, one thing is clear from here, that the conditional probability mass function or conditional probability density function is proportional to the joint PMF or PDF, because this kz is a fixed quantity, because z is a fixed quantity. So, it is a function only through f of yz yz. So, that means what we conclude is that the conditional PDF or PMF is always proportional to the joint PMF or PDF. This is a very nice observation, and it helps us in many situations to find the conditional probability density function or probability mass function directly from the joint PMF or PDF. So, now let me give the definition of a conditional expectation. You see what we have done, we have said conditional expectation is nothing but integrate the corresponding random variable along with its probability mass function or probability density function. So, similar concept holds for conditional PMF or PDF. So, if I am integrating the variable with conditional PMF or conditional PDF for a fixed value of the conditional variable, I get the conditional expectation. So, let psi from Rp1 to Rp be a given function, and let z belonging to Sz be such that Fzz is positive, and suppose this z is fixed. The conditional expectation of psi y given z is equal to z is defined by, so conditional PMF or conditional PDF of psi y given z is equal to z is nothing but integrate psi y, because z is fixed, along with the conditional PMF or PDF of y given z for a fixed z. So, we are integrating with respect to y, because y is the variable over here. So, this is how the conditional expectation is defined. Now, similarly I can talk about conditional variance. So, the conditional variance of psi y given z is equal to z is defined by, that means you talk about the variance of conditional distribution of psi y given z is equal to z. So, that means variance of psi y given z is equal to z is nothing but, by definition, what is the variance of t? Variance of t is nothing but expected value of t minus expected value of t, this whole square. But here I have to do all this with respect to conditional expectation. So, this expectation is also conditional expectation. So, that is why this expectation given z is equal to z. Then this expectation also has to be with respect to conditional expectation. So, that is why x value psi y given z is equal to z. and t is a variable psi y. So, that is psi y exclusive psi y minus exclusive psi y given z is equal to z. It's so this variable minus its mean with respect to conditional distribution, then the whole expectation with respect to conditional distribution. So, that is how you define variance of psi. And I know that variance is nothing but expected value of t square minus expected value of t whole square. So, this would be same as exclusive psi square y. The only thing is I have to take it with respect to conditional distribution of y given z is equal to z minus expected value of t. So, expected value of t again has to be with respect to conditional distribution of y given z is equal to z. So, expected value of psi y given z is equal to z, its whole square. So, it is a obvious extension of a definition of a expectation. Here the only thing I am doing is I am considering the conditional PDFs or PMFs to define the conditional expectation. Now, one thing is clear from here, because here this small z is fixed. So, expected value of psi y given z is equal to z is a function of z. So, as you vary z, this quantity changes. So, it is a way to interpret this would be, for example, if you are considering the joint distribution of height and weights, and I say that what is the mean height of all those students whose weight is 80 kg. So, in that case weight may be z, and that is had been fixed at 80 kg. What is the mean of height of such students? So, that gives me conditional expectation of height given weight. So, let me introduce a notation. When I write down expected value of psi y given z, so here z is a random variable. So, it would be a function of this z. So, this is psi star z, where this psi star z is nothing but psi star at a fixed point z is nothing but expected value of psi y given z is equal to z. So, when I say expected value of psi y given z, what it says is find out first expected value of psi y given z is equal to z, which is psi star z, and then you replace that fixed z by the capital Z, then you get psi star z, and which we use the notation as expected value of psi y given z. So, similarly we can define variance of psi y given z. So, what it means is, while defining variance of psi y given z, it is nothing but, let me call that as k of z, where k z is nothing but variance of psi y given z is equal to z. So, I am calling this as a function k of z, where k at a fixed point z is nothing but variance of psi y given z is equal to z. Now, similarly I can define covariance of y1 y2 given z, correlation between y1 y2 given z. So, all these wherever I have to find a variance, mean, correlation given z, I have to use the conditional distribution of y given z. So, one thing a very useful result sometimes, it says under the above notations, if I have to look at expected value of psi y, that is same as expected value of conditional expectation. So, expected value of conditional expectation of psi y given z. It is like this. Suppose you have a height and weight, and I mean of students, right. So, you have two variables. Let me call this as y, this as z. I have to find the mean height of students in a population. So, let me call that as psi of y. So, what it says is to find the mean height of students in a population. First you fix the height, first you fix the weight. So, let us say among all students having weight 80 kg, take their mean height, then keep on varying this weight and taking their, and then finally you take the mean of all this. So, this is same as expected value of conditional expectations. So, that means first you fix weights, take the mean, and then finally take the overall mean. So, expectation of psi y is same as expectation of conditional expectation. Now, similarly variance of psi y is same as variance of conditional expectation plus expectation of conditional variance. So, if you have to find the overall variability in the height, what it says is first find what is the mean for a fixed set. So, find all this, look at the variability between the means for a fixed, for various values of fixed jets, plus it will be same as, then it says you look at what is the variability within each jet and look at what is the average or the mean variability within each group. So, variance of psi y is same as variance of conditional expectation plus expectation of conditional variance. So, note that this quantity is nothing but psi star z. So, this is same as exclude psi star z. And what is psi star z? Where for fixed z belonging to S z, psi star z is nothing but exclude psi y given z is equal to z, which is same as integrate psi y with respect to conditional PDF of y given z is equal to z. So, this is same as psi y conditional PDF of y given z is equal to z. So, now I have to find exclude psi star z, exclude psi star z. This is nothing but integral over psi star z and then f z z dz. Psi star z I have found out this. I have to integrate it over here. So, I put one integral and then f z z z, and that is what I do next. So, exclude psi y given z is exclude psi star z, which is same as psi star z f z z dz. This psi star z we have seen is this quantity z z dz. So, it becomes integral over r p 1 integral over r p 2. So, that becomes integral over r p, because p is same as p 1 plus p 2 psi y f y z into f z z dz. But this quantity together is nothing but f y z y z. Why? Because f y given z y given z is same as joint PDF divided by marginal of condition, which is f z z, and f z z was anyway sitting over there, that gets cancelled with this and you get f y z. But this is nothing but exclude psi y, and that is what you have to prove. That means exclude psi y is same as expected value of conditional expectation of psi y given z. Let us go to the similar formula for the variance. So, let psi star z is exclude psi y given z. Then by A, variance of psi y is nothing but exclude psi y minus is expected value of psi y, take whole square and then take the expected value. Now, if I use the result of part A, it says expected value is same as expected value of conditional expectations. So, this same as expected value of this and then expected value of this given z. Let me call this inside quantity as psi 1 z. So, this same as expected value of psi 1 z. Now, I look at what is psi 1 z. Psi 1 z is this inside quantity, which is nothing but expected value of psi y minus expected value of psi y whole square given z. So, what I do is I add and subtract over here exclude psi y given z. So, I add and subtract that. So, minus psi y given z plus psi exclude psi y given z and minus exclude psi y whole square given z is there. So, this is, let me call this as A, this as B. So, this is A plus B whole square, which is same as A square plus B square plus 2 times AB. So, I expand that. So, that becomes, and then expectation is linear. So, expected value of A square plus expected value of B square, which would be this quantity. But note that here z is fixed. So, exclude psi y given z minus exclude psi y, when I take its expectation with respect to conditional PDF of given z, for a given z this is a fixed quantity and this is anyway a fixed quantity. So, when I take expected value of this quantity with respect to conditional PDF of y given z, I get this itself, because for a fixed z it is a fixed constant, plus 2 times cross product of these two. When I do get the cross product of this, anyway this is a constant. So, 2 times exclude psi y given z minus exclude psi y, then expected value of just this quantity, which is psi y minus expected psi y given z, which is same as, now let us look at what is happening over here. This is psi y, you are taking it expectation with respect to conditional distribution of y given z, its square, and then you are looking at conditional distribution of y given z only. So, this is same as variance of psi y given z, plus this is same as exclude psi y given z minus exclude psi y I write down as expected value of conditional expectation further. So, this same as this whole square. Now, let us look at what is this quantity. Here for a given z, this is a fixed quantity and these are random variables. So, this will become expected value of psi y given z minus this constant quantity, which is same as this quantity expected value of psi y given z, because for a fixed z this is a fixed quantity, because this would be a function of z, but when you are taking the expectation over here and z is fixed. So, this is a constant. So, this becomes exactly same as this, they get cancelled and you get 0. So, thus from 1 variance of psi y would be expected value of this quantity, which is same as flu of variance of psi y given z, plus expected value of this quantity, which is expected value of flu psi y given z minus flu of flu psi y given z whole square. So, this same as expected value of variance of psi y given z. Let us look at what is this quantity. Here, let me call this expected value of psi y given z as psi 2 z. So, this same as expected value of psi 2 z minus expected value of psi 2 z whole square. So, this is nothing but variance of this quantity, which is nothing but variance of expected value of psi y given z. So, what you get is variance of psi y is same as expectation of conditional variance plus variance of conditional expectation. So, sometimes this formula is quite useful.